Let me show you how to be a good breezy and change your predictions.
Welcome to another installment of our LBS Physics Deep Dive. After exploring the world of experimental physics at CERN in our first video documentary in episode 93, we'll stay in Geneva for this one, but this time we'll dive into theoretical physics. We'll explore mysterious components of the universe, like dark matter and dark energy. We'll also see how the study of gravity intersects with the study of particle physics, especially when considering black holes and the early universe. Even crazier, we'll see that there are actual experiments and observational projects going on to answer these fundamental questions. Our guide for this episode is Valerie Domcke, permanent research staff member at CERN, who did her PhD in Hamburg, Germany, and postdocs in Trieste and Paris. When she's not trying to decipher the mysteries of the universe, Valerie can be found on boats as she's a big sailing fan. This is Learning Bayesian Statistics, episode 95, recorded September 6, 2023.
Let me show you how to be a good breezy and change your predictions.
Hello, my dear Bayesians. Some of you have reached out for advice and coaching in parallel to my online courses on intuitivebase.com. So, to help you, I have started something new. If you go to topmate.io/Alex_Andorra, you can pair your online course with my 15-hour or 20-hour coaching packages to get a fully premium learning path. Each week, we'll get on a one-to-one call and we'll walk through any question, difficulty, or roadblock that you may have to jumpstart your learning even more. Again, that's topmate.io/Alex_Andorra. And now, let's talk theoretical physics with Valerie Domcke.
Let me show you how to be a good breezy and change your predictions.
Valerie Domcke, willkommen nach Learning Bayesian Statistics.
Glad to be here.
Yeah, thank you for taking the time. I am really happy to have you on the show. Again, a physics-packed episode. So I'm really happy about that. And I have a lot of questions for you. I think you're the first theoretical physicist to come on the show. So that's cool. We're gonna talk about topics a bit different than those we talk about when we have experimental physicists on the show. So that's cool. More diversity for the listeners. And also, when that episode is going to air, by the magic of time travel, episode 93 will have been published. So that's the one at CERN. So the very special video documentary I did at CERN with Kevin Greif. So if listeners haven't checked it out yet, I highly recommend it. And that one, of course, I recommend mainly watching the YouTube video, because I recorded and edited it firstly for video format. You have access to the audio format also, but I'm telling you, it's going to be funnier in video. So now, to actually complete what we talked about in episode 93, where Kevin does a lot of fun experiments at CERN, today we are going to talk about another part of physics that's done at CERN, thanks to you, Valerie. But first, before doing that, let's start with your origin story. How did you come to the world of theoretical physics, and how sinuous of a path was it?
It was more of a path that I kind of ended up on without honestly thinking about it too much. It's kind of been a topic that has fascinated me since I was quite young, reading science fiction books and the like. And I basically was just kind of following my interests, taking the courses at university that interest me most without thinking too much about where that would lead me in the end. And it was basically only when I was doing my PhD that I realized, wow, I'm actually working on cosmology and kind of these big open questions of the universe, which is something I was dreaming about as a kid, and somehow I got there without too much planning, but just following what I thought was kind of the most interesting thing for me to do at every step.
Oh yeah, so it's really like the the call of passion for you.
In a sense.
Yeah, no, that's really cool. I mean, and that's also one of the cool things of this kind of job, right? In physics, or I don't know, airplane pilots, or firefighters. You can dream about them already as you're a kid, and then make that your job. I personally love my job, but I'm afraid I cannot say that I dreamt about Bayesian statistics when I was a kid. Like, I never told when I was 5 years old, "Oh, I want to be a Bayesian statistician." It's not how it works, unfortunately.
Really?
Yeah, no, I know. That must be quite disappointing to a lot of people, but I had to burst that bubble because I get a lot of questions about that. Yeah, so.
Yeah, I would also say that you kind of have to really dream about it or really be enthusiastic about it, because doing science, you always encounter moments when nothing works.
Yeah.
And if you're not passionate about actually solving the problem, you're just going to get stuck.
Yeah. No, definitely. That's a very good point, and that's where actually statistics get back in the mix, because I would say that's the same for programming and the kind of statistics, at least I do, where you are gonna get a lot of bumps along the way, and I always say to beginners that models never work. Only the last version, the last iteration of a model is gonna work, and even then, you just have to be satisfied with good enough. So that's a field where you have to become comfortable failing all the time. First, be comfortable with making mistakes and failing, and also where you need to be driven by passion, because if you don't have that inherent passion, you're not gonna still be driven to solve those numerous data analysis issues and bugs and stuff like that. So now I'd like to talk about what you do, actually, what you're doing nowadays, because we know you dreamt about doing that since you were a child. But how would you define the work you're doing nowadays, and what are the topics that you are particularly interested in?
Right. I think there's probably two parts to that question, right? One is kind of how does an everyday day actually look like, and the other one is, okay, what are the big topics I'm interested in?
Yeah.
So to start with the former, so what my day does not look like is that I kind of sit in my office all by myself, waiting for the fantastic idea that is going to win me a Nobel Prize. That's kind of the image I had maybe as a kid of how a theoretical physicist would work. But that's not at all what my day looks like, right? So it's a lot discussing with people, listening to talks, going to conferences, reading papers, discussing over coffee on the blackboard over lunch, and then progress comes bit by bit. But it does kind of, there's never a lack of things to work on. There's never a lack of interesting questions. There's only always a lack of time to decide what is the most interesting question of all the questions to work on, because there's really a lot of things that we don't understand. And that brings me a bit to the overarching theme of my research. So I work on the intersection of particle physics and cosmology. So meaning kind of the physics of the very, very smallest particles, the fundamental building blocks of nature. And at the same time, the physics of the very largest scales. So the largest scales we can observe in our universe. And how the latter can teach us something about the former. So how kind of from astrophysical or cosmological observations, we can learn something about what is really the nature of the fundamental building blocks of nature.
Yeah, so small topics, fundamental building blocks of nature. Yeah. Yeah, thanks. That was that's interesting. I'm actually curious. So of course we're gonna talk about your the projects you work on a day to day a bit more. But also I'm curious now that you brought up basically what your days look like concretely. Yeah, I'm wondering what's the part of, basically solitary work with pen and paper. What's the proportion of that in comparison to, as you were saying, collaboration with people, exchange of ideas, and things like that? Because I think when you tell people you're a theoretical physicist, and that's definitely the case when you tell people you're a statistician, most of the people imagine that you're just doing math on a blackboard. So most of the time, which is not true if you're a statistician. So yeah, I'm curious how it is on your side.
Yeah, it's probably similar. I mean, if I get 1 or 2 hours on block to actually sit down and do a calculation, that's rather the exception than the rule. So it is, of course, part of my job, and I enjoy it a lot. Like sometimes just to have time just to think really thoroughly about a problem, either analytically, so pen and paper, or coding. But it's usually not like very long stretches at a time, because then you hit a problem, right, or you hit a solution. And in either case, that's the point, to reach out to your collaborators and discuss the next steps.
Yeah. I mean, that's interesting, because for me, now I'm using more and more the excuse of teaching to dive deep in a topic, in a project, because well, I have to be able to explain it properly to students. So these are actually the good occasions, and quite rare occasions, where I can just be myself working on the computer, or sometimes with a pen and paper, and really understand deeply a topic that I need and want to understand. Because otherwise, yeah, you have so many other projects and solicitations that can be hard to actually take the time just for yourself and focus on these. So I'm the same. Yeah, I do appreciate these solitary moments, although I'm happy that they are not 90% of the work, I have to say.
Yeah, same here.
And actually, so you're a very math savvy person, so of course you know about Bayesian stats. But I'm curious if you were introduced to Bayesian methods, actually, in your graduate studies or before, and if you use them from time to time in your own work.
No, so I never received any type of formal or informal training. So it's of course it's something we need to know, in the sense that we deal with empirical data. Even if I myself don't usually deal directly with the empirical data, but I kind of deal with the processed empirical data, or I deal with the publications that people have written on the data, and then I need to evaluate, interpret, and kind of continue to work from there. But for that, of course, I need to kind of understand the significance of certain experimental results.
Mm-hmm.
So I would say, I mean, I have a fundamental understanding of them, right? But it's not something that actually kind of on a day-to-day basis I'm like deep in the details of it.
Mm-hmm. Yeah.
Because I more work at the kind of one level away, right? So kind of that I kind of take. I need to understand what is the significance of that result, right? But once I've understood that, I can basically work directly with the result without having going back to the data at every step.
Which is quite a luxury, I have to say. I'm a bit jealous.
Yes, I'm very, very happy that there's people who do the work that I don't need to do.
Yeah, no, that's a very good point. I like that. And if you go listen to episode 93, you'll see the difference between basically that kind of work that Valerie does and the experimental physics work, where statistics is way more present, and of course Bayesian statistics is extremely helpful. So I find that super interesting to notice. Just because you don't use Bayesian stats, Valerie, doesn't mean that your work is not interesting. I have to put that out there. On the contrary, I find it fascinating. So let's dive in, because one of your areas of interest is to go beyond the standard model phenomenology to kind of probe it, if I understood correctly. So can you tell us what that means, and maybe first define the standard model for us?
Right. So the standard model basically reflects our current understanding of these fundamental building blocks of nature. So it kind of contains what we think are kind of like elementary particles, which are no longer further dividable into even smaller particles. And there's not many of them. There's basically a handful of them, depending how you count. And we think that these fundamental particles, together with the interactions between these particles, that they explain all of kind of nature, the way it surrounds us, right? So everything that we can grasp or experience here on Earth. And the standard model describes basically this. So it describes kind of which building blocks are there and how do they interact with each other. And now going beyond the standard model, because a model is always a model, right? So it means it describes kind of nature to the best of our knowledge. But most models are incomplete at some level, right? Because it's kind of only a way that we describe nature, not actually the fundamental theory of nature. And for the standard model of particle physics in particular, it does extremely well in many respects. One could even say frustratingly well, because like in all our searches of looking for new interactions, looking for new particles here at CERN, at the Large Hadron Collider, we always keep confirming the predictions that the standard model makes with incredible accuracy. But we still know the model is not complete. And the reason we know that the model is not complete basically comes from cosmology. So there's observations that we make about the dynamics of the universe, or the properties of the universe, which are simply in contradiction with this model, which tells us that there's ingredients missing. And we have a rough idea of what these ingredients are, or rather maybe instead of one rough idea, we have 100 rough ideas. And the big question is, which one of these is correct? Is any one of these correct? And how can we make progress in understanding these missing parts better? So to give you some keywords, things like dark energy, dark matter, those are some of the open questions.
Yeah, because we know, basically, you say they are open because first, we cannot really explain them fully for now, as we said in episode 93, but also we know that the standard model breaks down at those at those points and cannot explain them, right? So that's basically what you're trying to understand. Why does the standard model fail here, and how can we actually explain these phenomena?
Correct.
I see. Yeah. And so concretely, what does that research look like? Maybe could you share an example of a discovery or a theoretical development in this field that has the potential to reshape our understanding of particle physics?
You mean like a discovery in the past that did that, or a potential discovery in the future that
I would say both.
Potential?
Yeah,
okay.
Both if you can.
Let's start with the past. So one observation, for example, was rotation curves of galaxies. So people were looking at galaxies in the sky, and they were looking at kind of how fast the stars were rotating, which you can do by measuring the redshift of the stars, because as they move away from us, the light gets slightly redder. As they move towards us, the light gets slightly bluer.
Yeah.
And if you know, like if you have an object on a stationary orbit, and you know the orbit, you know the velocity. I mean, actually, even knowing the orbit and the mass of stars enough, then you can kind of estimate how much mass you need in the center in order to kind of make that a stable orbit. And so that's just Newton dynamics, high school physics. And what people observed is that the mass that you needed in the center in order to kind of put these stars on the orbits that were being observed was much, much bigger than the mass you would have inferred just by counting stars.
Mhm.
And now you can say, okay, well, counting stars is obviously not enough, right? Because there's going to be planets. Planets are not luminous. So there's going to be a bit of an offset. But you would have expected that counting stars would give you a good estimate. And it turned out it was completely off. So it turned out it was kind of a big amount of something that has an attractive gravitational force
Mhm.
kind of in the center of the galaxies, or like in a halo around the galaxies, which was invisible to our telescopes. And that is basically what then coined the term dark matter, because it kind of has a gravitational pull of matter, just
Yeah.
like everything else. But it's dark, meaning we can't see it. And not seeing it means like not only kind of we don't pick it up with telescopes, but kind of also all other type of experiment that we've performed to date, trying to find this stuff. And this stuff should be around everywhere, right? So it's not that there's none of it on Earth. It's just that it's so incredibly weakly interacting with
Yeah.
all the instruments that we build that it's very difficult to see. And then observations, more observations, particularly cosmological observations, revealed that there's actually 5 times more of this dark matter than there is of what we call ordinary matter, right? So ordinary matter is everything that we know of on Earth and everything that we can describe with our standard model of particle physics. Meaning that there's really a lot of stuff out there that we don't know what it is. That's just one example.
Yeah.
And that kind of gave very clear indication that the standard model of particle physics is incomplete, and that we're not only missing a little bit, but that we're actually missing a very big bit of the picture. And along the same line of thought, what would really be a groundbreaking discovery if one of the many experiments looking for such a dark matter particle, if they would actually find something. Even if they don't find anything, if a particular experiment doesn't find anything, then okay, you've still learned something because you can probably exclude some class of models.
Yeah.
But if one of them actually made a discovery, and we would have kind of a very clear indication of which direction to go in when we're kind of trying to describe these dark matter particles, that would be a complete game changer.
Yeah, for sure. And so these kind of experiments are underway at CERN in particular, right? These days.
Yeah, at CERN and across the world. It's something you can look for when in a collider, because you can always hope that if as your collider reaches higher and higher energy, or you have kind of just more and more particles that you're colliding, you'll eventually kind of reach the threshold for producing these particles, and then you can find indirect traces of them in the decay channels, or you basically have some sort of not a collider, but basically just a very big detector volume somewhere. So a very big amount of a noble gas, for example, or even water. And then you wait basically for a dark, you have to shield it very well against everything else. And then you wait for some dark matter particle to have one of these very rare interactions with one of the atoms of your detector. And you're looking for that interaction. And there's a range of experiments underway looking for very different types of these dark matter candidates. But we've been hoping that we'll find it any day now, basically since since I do physics. So we don't know. It could be around the corner, or it could be very well hidden.
Yeah, these kind of experiments, I think I would not be able to work on them at least full time. That's awful. Like you're just waiting for something and you cannot control anything.
There's plenty of stuff to do. You're not just waiting, right? Because you're basically constantly fighting to, reduce noise, reduce background, understand noise, understand background, argue with somebody who's making noise in the building next door, right? And is disrupting your experiment. So,
yeah. Yeah, no, for sure. That's that's something you have to deal with all the time, I guess. But yeah, I would be also, incredibly stressed out. Like, so did the I think a lot of them are helium pools, right, or something like that.
Correct.
So, did the helium pool move tonight or not. I mean, it's just, I would be incredibly stressed out. Yeah, so thanks a lot. That's actually very interesting to hear about that, because I find this kind of experiment absolutely fascinating. And where does your work come into that picture? Personally, what kind of those? So you're part of these big teams, right? In physics, like you see a physics paper, it's like most of the time a lot of people, because a lot of you are very many of you are very specialized in what they do, and so you bring one of the brick to the paper. So you, in this kind of work, what do you do? What do you bring?
So the papers really with like the many hundreds of authors, they're usually the experimental collaborations. Mm-hmm. So as a theorist, I usually have whatever 2, 3, 4 co-authors on a paper.
Not a lot.
Right. So we build, of course, very heavily on the results of these big collaboration papers. Mm-hmm. But largely the work that I concretely do is with much smaller groups of people. Mm-hmm. So I basically have two main approaches to this. One is kind of starting from really standard model of particle physics and trying to come up with possible extensions of that, which kind of makes sense within the framework that the standard model is written in. So makes sense within the symmetries that there are, makes sense within the framework of quantum field theory, and address some of these open problems that we have in cosmology. Mm-hmm. And then the question is, okay, once you've kind of constructed such an inherently consistent model, what sort of implications might that have in various types of experiments, right? So that can be experiments like the Large Hadron Collider. It can also be some astrophysical observations, or it can be some cosmological observations. So that's kind of one approach, and coming kind of more from the fundamental mathematical theory of it. Mm-hmm. And my other approach is more the lamppost approach, meaning, well, you look where you can look, right? And you hope that nature is kind. And there kind of my approach is to say, okay, what types of probes do we have of the universe, of astrophysical processes? Mm-hmm. Try and understand as much as possible about those, and then see what type of models or what kind of types of building blocks of models you could test with these types of observations. And there, for example, the new big player in the game are gravitational waves. Yeah. Because now, since the first discovery with LIGO, and now a tentative discovery in a different frequency range this year with the pulsar timing arrays, that's kind of opening up a completely new way of observing our universe. And so there's the potential for big excitement in that field. So I'm also just involved in trying to understand as much as possible about how gravitational waves can reveal something about the universe.
Oh yeah, so that's actually fascinating. So yeah, like, talk to us a bit more about that. Basically, what can gravitational waves tell us about the universe, and maybe redefine quickly what gravitational waves are for listeners.
Right. So gravitational waves are, we think of them as perturbations of the metric, so perturbations of space-time. Mm-hmm. So the type of gravitational waves that we've already seen with LIGO and Virgo, which are big Michelson interferometers. So the type of gravitational waves we've seen come from pairs of black holes, which are circling each other and then finally merging. So these are like extremely massive objects. And as you might know, kind of a massive object kind of creates, if you want, a dent in space-time. And if you have two of them, just kind of their dance around each other really like sends out ripples of this kind of space-time perturbations out into the universe. If you're very close to a black hole, right, these ripples will be quite significant, but then you'd also have all sorts of other problems, right? Because if you're really close to a black hole, then you have a lot of problems. So by the time these gravitational waves reach us, they've kind of spread out very far, meaning the amplitude is very much decreased. So by the time they reach us, these are typically very, very small, like tiny perturbations in space-time.
Mhm.
So it's not something we have to worry about in everyday life. Rather, we need to build an extremely sensitive detector to even pick them up. And so far, the observations that we've made are this type of observations. So observations of these black holes merging, which happened, I mean, still at the distance of megaparsecs or gigaparsecs from here, right? So it kind of quite far away on cosmological scales, but nevertheless, kind of compared to the lifespan of the universe, these are still fairly recent events. So at the moment, we're using this to learn, because it's a new way to learn about kind of the universe surrounding us, or the more recent universe, or the relatively recent universe. Whereas the promise is, or the hope is, that in principle, because these gravitational waves are so weakly interacting with everything, in principle, even gravitational waves generated in the very, very early universe, when the universe was not yet transparent to photons, when kind of no other messenger could escape this primordial soup, gravitational waves could. So in principle, if we detected them today, they could reveal information about extremely early times in the universe, when the temperatures in the universe were extremely high, when all the fundamental particles kind of existed as fundamental particles, and when we can really kind of probe these constituents of the standard model, or of any model beyond the standard model. So that's the ultimate hope. But it's challenging because we don't know what is the amplitude of these gravitational waves from the very early universe. And so we first need to understand the gravitational waves generated in the late universe. Make sure we fully understand that before we kind of look for a fainter signal. Very similar to with photons, right? You basically first need to kind of understand all the light kind of coming from the nearby universe, coming from the galaxy. And only when you have a very good understanding of your foregrounds can you go and can you look for fainter light that is coming from earlier times.
Yeah, that makes sense. Because also those waves are like so much weaker that also I'm guessing you have to be a bit more aware of what you're looking for, because otherwise it's even harder. And to understand, like, do we know if just one black hole, for instance? So, for instance, the black hole at the center of our galaxy, is it emitting also gravitational waves? But since it's not orbiting another one, at least that we know of, the gravitational waves are weaker, so we cannot see them? Or do we know that, no, you have to have the collision of two massive objects to get those gravitational waves?
Yeah, so a single black hole won't do it, because anything that is perfect spherical symmetry won't do it. That has to do with the fact that these gravitational waves are tensor modes, right? So they have two Lorentz indices, and that's something that's spherical symmetric is a scalar quantity. So a single black hole won't do it. So you need two, or you need a black hole and another massive object, say a black hole and a neutron star. Or anything else that breaks spherical symmetry, right? So kind of, I don't know, you dancing around, right? That will in principle generate gravitational waves. They're just very, 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 very small.
Thank you. I'm flattered. No, yeah, I see. Okay, yeah. So it's very it's really the density of the objects that count. Like, yeah, I cannot even imagine
a large concentration of mass, and in some asymmetric way. So some sort of violent process which is condensing a lot of energy, a lot of mass.
Yeah.
But in some way that is moving in a bit of a non-trivial way.
Yeah, that makes sense. Even though I like thinking about these things because it's so hard to imagine. Like the power of these collisions must be just incredibly devastating. I would love to see that in a way, but that's it's really impressive and at the same time really frightening.
Yeah. So the gravitational waves that we saw with LIGO, there we think it's something like two black holes roughly of the mass, like roughly 10 solar masses each, colliding. A bit more. And the energy that is just the energy that is released into gravitational waves corresponds roughly to the mass of our sun. So it's a huge amount of energy. And now the gravitational waves that we think we might have seen with these pulsar timing arrays, these are even more massive objects. These are really the large black holes, right? Like the one in the center of our galaxy that we think we see colliding. So this is two far away galaxies, each with their big, massive 10 to the 6 solar mass black hole in the center. And when they collide, that's the signal that we expect. So that's a massive event, right? I mean, two galaxies colliding. You don't want to be close to witness that.
Yeah, no, that's for sure. And so these are absolutely fascinating topics, and I'm wondering, what are the main challenges in understanding these topics right now, and how do you folks as researchers in this field address them?
That's a broad question, right?
Yeah, that's a very broad question.
I mean, there's different levels of challenges, right? So when it comes down, for example, to let's say something concrete, like understanding these signals, which we think might be from gravitational waves, then I mean, a lot of the problems boil down to making sure this is a signal and not a background or a noise source. So that means, of course, building experiments that are extremely precise measurement devices. It also means a lot of modeling of the various components that go in, and kind of both from the theoretical side and also from the experimental side. And then when you get the data, again, to cross-check, okay, is this really the type of signal? Do we have a robust way to distinguish what we call a signal from something that we call a background? Take it into account that we might not have thought of every possible background, right? So do we kind of really have a telltale signal of what we think the signal would look like, right? And typically all these analyses are done as blind analysis, right? So you think about what signal you need to see in order to be convinced that this is what you're looking for before you open the box and look at your data. So that's one challenge, more kind of on the data analysis or experimental side. The other challenge maybe more on the theory side. So when you're kind of building models which extend the standard model of particle physics, there's many options, and you need some sort of guiding principle. And I mean, if you're lucky, you have data to guide you. You have some sort of anomaly, something you feel like, okay, here's the weak point, right? Here's kind of where you need to poke, where you need to extend. Sometimes you have things like simplicity, right? Which you kind of hope is a good principle, though of course you never know that that's a good principle. And recently, that's really been a bit of a challenge, precisely because the standard model works as well as it does. There's no, I mean, sure, we know we need to explain dark matter, right? But there's many possible options how that dark matter could or could not tie into the standard model. And there's no very obvious way, there's no obvious weak point at the standard model. There's no precise weak point. I mean, there's a global weakness, things it cannot explain, but it's kind of not quite clear where exactly it needs to be refined or extended. And that, I think, for in the past, it was more clear, or people had pretty clear ideas, right? And then there was pretty obvious things that needed to be checked, right? So we needed to find the Higgs particle, right? So the last missing particle of the standard model. And then we also thought, because the Higgs particle has certain properties which kind of led us to believe that we thought, okay, once we find the Higgs particle, we should also be finding other particles somehow related to this particle that would naturally explain certain open challenges. But the fact that we haven't found them and that we're just kind of testing with higher and higher accuracy, and we're just kind of getting the predictions of the standard model or confirming the predictions of the standard model without finding any small deviations is making it very hard to kind of decide a bit how should the extension work, right? And how should the extension like is the extension in such a way that we can actually test it with the tools that we have, right? Or do we need to think differently? I mean, either different types of experiments, but also maybe different theoretical concepts, because so far most extensions of the standard model kind of rely on the same theoretical framework, quantum field theory, and then they kind of within that framework you try different things. But the fact that kind of we haven't had a real breakthrough there may be indicating, okay, whatever, it's just at higher energies which we can't reach, or it may be indicating the framework we're thinking in is maybe not the best. So yeah, there's many questions, many levels of questions.
Yeah,
that can be addressed.
Yeah, that's really interesting. And how I'm curious, basically, what would you like to be true? Like if you could choose something that at some point nature will tell you, what would you like to see and to observe, and the kind of consequences it would have on our understanding of how the universe works?
Well, I would mainly like nature to produce something that we can, like, give us something to work with. I would like nature to be kind enough to produce some sort of signal, be it in dark matter, be it in gravitational waves, be it at a collider, that actually gives us something which is accessible with the tools, the experiments that we have at the moment. Because it could simply be that all these completions of the standard model live at an extremely high energy scale, which is simply inaccessible to any type of collider we can build on Earth. And that'll make it not impossible, but very, very much harder to actually unravel these questions.
Yeah, for sure. And that, I mean, so that's one part of the work you're doing, right? All that work around gravitational waves, which are, of course, related to gravity, in case people didn't understand. Oh, and by the way, on the podcast, I had another researcher called Laura Mansfield, and she's working on gravity waves, which are not the same as gravitational waves, right? So that's quite confusing, but yeah, that's also actually a very interesting field of research, basically gravity waves and the relationship with climate, and that's all here on Earth. But that's also related to gravitational waves in a way, in the sense that it's big objects basically on Earth. So like the Everest or the Mont Blanc or all these big, massive mountains, which actually distort a bit the gravitational field around them, and that has impact on the climate. And how do you model that? And Bayesian modeling gets here, because that's really useful, because you don't have a lot of sample size. So yeah, I recommend listening to episode 64. I put that in the show notes. And I was fascinated by that, the fact that gravity, you can study that here on Earth, but also it has incredible effects in the universe and at masses that we cannot even imagine, right? With the collisions of black holes and collisions of neutron stars. So that's really something I find fascinating. And actually, can you make the distinction between a neutron star and a black hole for listeners? And yeah, why, so that they understand a bit the difference between both?
Right. So a neutron star is made of neutrons, meaning kind of it's a very, very densely packed environment of nuclear matter. And a black hole is even more denser, right? So a black hole is really the densest object that we can imagine. Yeah. Where kind of matter has really, any type of matter has really just collapsed into this object, and you don't care anymore kind of what it was initially made out of, right? If it just has one property, can also spin, but basically it only has one property, which is its mass, right? And then it may also have a spin if it's rotating, but it doesn't matter anymore what it was made out of. So one consequence of that is that if you have two neutron stars merging, as they get very close to each other, their gravitational force will slightly distort them. So they can be a little bit deformed, because despite that they are very, very, very compact and very, very dense, they can still be kind of slightly deformed as they get very close to each other. Whereas two black holes will really stay perfectly spherical as they approach each other. And so you can tell the difference between the two by looking at the details of the gravitational wave signal as you approach this merger event.
Okay. I didn't know that black holes stayed spherical even as they approached each other. Is that because they are so dense that they cannot be deformed?
Yeah, it's basically because they're so dense, and because in some sense, despite that they are physical objects in our universe, in some sense they kind of become a rather mathematical object.
Yeah. Like a perfect sphere that you cannot deform or do anything on. It's really weird.
Yeah. And it's crazy that we're actually seeing them, right? Both in these gravitational wave signals, as also then with direct observations with optical telescopes. As like this first picture of the black hole in our galaxy and in the neighboring galaxy.
Yeah. And so your work on gravity, I'm curious to understand, because here, obviously, when we talk about gravity is so weak that you have to have so massive objects to really see its effects, and also it needs a lot of time. So obviously here we're dealing with the largest scales of the universe. But you also work on particle physics, as you were saying, and you work at CERN, where particle physics is one of the biggest fields. So I'm curious, how does that study of gravity intersect with the study of particle physics, especially when we consider the phenomena you work on, so especially black holes and or the early universe?
Right. So, gravity is well, in anybody, who's, I don't know, fallen down the stairs, right, will not say gravity is a weak force. But indeed, right, on Earth, right, when we compare the force of gravity to the other forces that we have, so the forces that bind atoms together, things like that, gravity is extremely weak. So when we perform any particle physics experiment on Earth, we just completely neglect gravity, and we're not introducing any error in our estimations. Now, gravity can become important, as you say, either if you have some very massive objects like black holes, or if you have very far distances. Because here on Earth, we have so much matter interacting so strongly that we don't care about gravity. But the universe as a whole is actually pretty empty. So in most of the universe, there's just nothing. Leading order, there's nothing. And that means that on those scales, because there's no matter which has any interactions that are stronger, on those large scales, it's really gravity that is describing the dynamics of the universe. And so if we want to understand both kind of the dynamics of the universe today, but also extrapolating back in past, if we want to understand the evolution of the universe, the birth of the universe, then we need to understand gravity. And one of the big puzzles, for example, is that at the moment, observations tell us that we are in a phase of the universe where the universe is not only expanding, but expanding in an accelerated way. And that's pretty weird, because normally you'd think if you just have a bunch of matter, right, bunch of galaxies, you'd think that, well, they're going to have gravitational interactions between each other. So even if you somehow gave them some initial velocity, you would think, okay, well, they're going to kind of slow down and eventually crunch back together again, because on those large scales, it's only gravity that is important. So on those large scales, you think you can either have things collapsing, or you can have kind of things, at least if they're expanding, they should be slowing down. But what we observe is the opposite, right? What we observe is really the further things are away from us, the faster they are moving away. So we're in a universe which is expanding faster and faster. And that is also gravity driving that. It's just not the kind of the usual form of gravity that we know on Earth, that gravity is attractive. But in some sense, you can call it a repulsive force of gravity, or it's a part of gravity that kind of acts as a pressure that drives the universe apart. And that is what we coin dark energy. So again, the term dark just implies we don't really understand and we can't see it. And energy basically comes from observations that it has this effect of driving the universe apart. So it acts as a type of energy in the expansion history of our universe and concretely today. But we don't really, so we can model it, but we don't really fundamentally understand what it is. And so understanding that and understanding kind of how the universe evolved, not only today, but in the past, that then immediately ties back into particle physics, because going back in time in an expanding universe means you go to a smaller universe where everything was much more dense, much more hot. You end up in this primordial soup of particles. Yeah. So you're looking at particles at high temperatures, particles when they're really kind of not bound in atoms and molecules, but when they exist really in their fundamental nature. And that's basically a lab to study particle physics. So that's how the connection works between these very large scales of the universe and then the very smallest particles that we study in that way.
I see. And yeah, it's because you're going back to the early universe where basically the structure that we have today of the universe didn't apply because it didn't exist yet.
Correct. We go back to when everything was really kind of just this hot primordial soup of fundamental particles. We try to understand kind of how different properties of this soup, meaning different possible extensions of the standard model, would kind of leave traces in the evolution of the universe, so would leave traces in kind of astrophysical and cosmological observations that we can make today.
I see. And these days, what's a specific experiment or project that you're involved in this field, and what would be the main question that this project is trying to answer?
Right. So a big project I'm involved in, right? So this is many hundreds, thousands of people working together, is the LISA project. So that's a future space-based gravitational wave observatory. It's going to be an ESA mission. The idea is to have 3 satellites circling around the sun on an orbit similar to the Earth. So following Earth on an orbit around the sun. These satellites will be 2.5 million kilometers apart. They will exchange laser links. So they will be lasers going between all combinations of the satellites. And using these lasers, the idea is to measure very precisely distance between these satellites as they orbit the sun. And the idea is that if a gravitational wave comes, since it's a kind of little ripple in space-time, it will change very slightly the distance between the satellites. And so by kind of looking for these little variations in the distance between the satellites, the goal is to look for gravitational waves. And being in space has the big advantage that a lot of the noise that you have to deal with on Earth is not there. So the idea is that you can reach much better sensitivities than you could on Earth.
Yeah, that makes sense. Also, although I'm guessing the sun can be noisy at times.
Right, but it's all a question of frequency, right? So you need to kind of find a frequency band which is clean.
I see.
There's obviously huge technological challenges in implementing a mission like this, and many things that can go wrong. But this is why you need kind of really a lot of people with a lot of different expertise coming together, and also a lot of money to build an instrument like that.
Yeah, I mean, just the engineering part of because you have to launch 3 satellites. First, that's already hard. And then you have to put them in orbit around the sun, and that they still can communicate with each other. It's just, and they are extremely far apart from each other. So just that part is absolutely incredible that we can do that.
Well,
yeah.
knock, 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 right? I mean, we hope we can do it.
Yeah, I mean, but that's just incredibly fascinating. And so what's the ETA on this mission? When will the satellites go up, theoretically?
Right. So the hope is to launch in the early 2030s.
Mm-hmm.
Which seems a long way from now, but it's really not, because yeah, I mean, it takes a while to build a satellite, and also to develop all the kind of the data analysis pipelines that you need. Make sure you have all the sensors on board that you might need to perform whatever type of cross checks.
Yeah.
Make sure you didn't put anything on board which generates a bunch of noise. Because once it's up there, right? You can't.
Yeah.
I mean,
you cannot
it's
send.
not in.
Yeah.
It's
cannot
not
send
in Earth
anybody
orbit,
to
right?
repair it.
Exactly. You
Yeah,
cannot send anybody to repair it, right? So once it's up there, it's up there. So you really have to think of every possible complication beforehand.
Yeah, which is quite daunting. I have to do that for my own statistical models, where I probe them and I'm like, okay, where can the model fail? What could be the potential issues? It's already stressing me out, but then if you have to do that for something you cannot go back to, that's just incredibly daunting.
Right. If you think a code release is stressful, right? Then imagine this.
No, yeah. Oh my god. But so fascinating. I mean, and personally, what's your part in this project, for instance, in the LISA project?
Right. So I'm in charge of coordinating research on what we call the stochastic backgrounds. So these are the signals we talked about so far, in particular the ones we see by LIGO, are what we call transient signals, meaning most of the time the detector actually sees nothing, just noise, and then from time to time you have a relatively strong signal. You see it, then it's gone. So if kind of that's your data analysis challenge, then okay, you can calibrate your detector in the signal-free moments. You can learn all about your properties of the noise, and you can have a good noise model. And then when you get a signal, you can kind of do a pretty good signal-to-noise discrimination. Now, with LISA, the situation is going to be very different, because we're going to have, because it's such a sensitive instrument, we're going to have lots and lots of stuff going on all the time. So we're basically not going to have signal-free time. So we're kind of dealing with kind of measuring all these different signals and the noise at the same time. And at the same time, the idea is that we might have stochastic backgrounds. So stochastic backgrounds they're not transient signals, but it's kind of more like a white noise, which is there at all times. They could be coming from unresolved astrophysical sources, so unresolved black hole mergers that are kind of out of the range of our detector, so we can't individually detect them, but they just kind of contribute to some confusion noise. Or they could be these signals from the very early universe, which is of course the ones that I'm actually after. But so you have to kind of dig them out between all these loud transient signals, between these possible astrophysical noise-like signals, which look very, very similar to the kind of the cosmological noise-like signal that you would be looking for. And of course, look also very, very similar to instrument noise that you might have mismodeled or misunderstood. So what I'm working on is, understanding the possible models for these different components, in particular for the cosmological sources, but also trying to understand how could we, if we actually get some actual data, how can we actually disentangle all of these components, and how can we really kind of make the most of the mission, extract as much information as possible, with all these kind of overlapping signals and challenges.
Yeah. And I'm guessing that having to do that not in a few months is something you appreciate.
Yes. Yes. Yeah. So there's, I mean, yeah, there's many challenges on there. Obviously, many people working on it, and I mean, luckily, as you say, luckily we don't have to solve this in a couple of months, right? Because
Yeah.
we're basically also counting on things like computing power and so on increasing, new methods becoming available. But yeah, so it's but still, I mean, the development has to happen now, because if we kind of figure, okay, we need a certain type of sensor or some certain type of output data that would help us to discriminate these different signals,
Yeah.
we can't come along with that when the mission is already built, or even worse, already launched, right? So you kind of can't wait till you see the data to decide how you're going to do the analysis. You at least have to have a very good idea of how you're going to do the analysis before you see the data, and then maybe you can refine once you see the data.
Yeah, definitely. And so actually this kind of work that you do in theoretical physics, or that kind of project you just described, it really involves the development of models, of hypotheses, and I'm curious if you have some, favorite hypotheses or models, or the most intriguing theoretical ideas that you've encountered in your field, and that you'd like to see tested, and if we could actually test them right now with our current technology.
Good question. I must say, I don't have a particularly favorite model. Like, I don't feel, I don't know, protective or ownership of any particular idea. I'm more the type of person who I start working on something because I find it interesting, and then once I've understood it to a certain degree, I move on to the next topic. But I think there are a couple of kind of big overarching questions, right? So kind of understanding, getting some experimental input on what dark matter is would really help a lot on the theory development side. As I mentioned, when we also have issues understanding the Higgs particle, understanding in particular the mass of the Higgs particle, which is potentially indicating there's something we don't understand properly about quantum field theory, about really the framework in which we operate. That I find is incredibly exciting, because it would really mean kind of, okay, not an add-on, not a small extension of our existing model, but really a completely revolution in how we think about things.
Yeah.
Of course, it also makes it much more difficult, right? Because you don't even have the framework. Maybe we don't even have the mathematical framework to think about this. It's a huge step to take. So I mean, that's would really be a big step, right? So I'm not sure if and how that's going to happen, if it's even necessary, right? Maybe the current framework is totally fine, but that would definitely be a development that on the pure theory side, that would be very exciting to see happening.
Yeah, for sure. Definitely, I kind of I'm also really curious about that. And actually, is there one big question that you would like to see answered before you die? Your one big question that you'd really like the answer to.
I think I really would like to know the answer to dark matter, just because that it's well, we have many very reasonable models, which can be tested, and which are being tested. So we could still be unlucky, and nature could choose not one of these nice and reasonable models, right, but something completely different. But that's a field where there are some very good suggestions, and they can be tested. Now, unfortunately, there was one excellent suggestion, right, which was supersymmetry, and the dark matter particle that comes with supersymmetry, and would have was mathematically beautiful, would have solved a ton of questions, was in many ways the perfect theory, right? Unfortunately, we didn't find it. So it could still be out there, but kind of not as a solution to all of the problems that we hoped it would solve, because if that were the case, we should already have seen it. So something kind of being the ideal theory from our point of view doesn't mean nature actually cares, right? and does it that way. But yeah, so dark matter, I think it really has the potential that we could actually find it. And if we find it, that could really be a starting point of a whole new exploration of questions.
Yeah, definitely. And that's interesting that you mentioned dark matter too, because Kevin Clive, I asked him the same question and he answered dark matter too. So that's interesting to see that it's really something that's picking up in the physics space these days, where it seems like we're less, let's say, we're more hopeful that we can actually start making sense of it and probing the universe in a way that will give us some answers, at least, to this mystery. Whereas dark energy, from what I understand, we understand way less about dark energy than we understand about dark matter for now, right?
Yeah. That's correct. And also there we have much less. I mean, we see what it does on large scales, right? But we have also much less of an idea how to make progress. Both on the theory side, there's kind of not these kind of clear-cut models that kind of say, okay, here's a good theory of why it is how it is, and here's how you go test it, right? For dark energy, we have neither a clear-cut theory that kind of says, okay, here's a good explanation, nor any way of probing them, really. So it's much more in the blur.
Yeah. So hopefully in 10 days you'll come back to the show and we'll talk about dark energy and the latest progresses. So Valerie, I think I have so many more questions, but you've been already very generous with your time. So before closing up, is there any topic I didn't ask you about and that you'd like to mention?
I think we covered a lot, but nothing particular comes to my mind.
Okay, well, then I think we can call it a show. But as usual, before letting you go, I'm going to ask you the last two questions I ask every guest at the end of the show. First one, if you had unlimited time and resources, which problem would you try to solve?
Yeah, that's, as I said, that's actually a really tricky question, because we are in this situation that I find it very hard to pinpoint where is the weak point of the standard model, where should we poke it, right? So from the pure theory side, without any experimental input, I feel like if I had unlimited time and resources, I wouldn't engage on a single project right now. But I would basically just try and, gather as broad as possible understanding of as many concepts as possible, and hope that we will eventually get some sort of data which points us in the direction really to explore. I don't at the moment really have a clear-cut avenue where I say this is where I would put all my money.
Yeah. So wise answer where you don't put your eggs in the same basket. And second question, if you could have dinner with any great scientific mind, dead, alive, or fictional, who would it be?
Yeah, I think, we'd go for somebody dead, right? Just because that's a chance you don't get on a regular conference dinner. So I'd be really curious to talk with some of the people involved in the discovery of quantum mechanics. So say Heisenberg or somebody like that, because I feel like they were kind of at the core of the field when the field was also in a situation where it was kind of not so clear cut at that time, not even clear cut that there was a need to kind of extend the current understanding, because classical physics was well understood, right? And nearly all phenomena were very well understood, and people were thinking, physics, it's done, we understand nature. And it was just kind of very small tweaks here and there, right? That kind of were a bit confusing. So one could have easily believed everything is done and understood, go study something else. But they kind of opened the door to the world of quantum physics. And with that then came quantum field theory, with that came kind of elementary particle physics, with that came kind of all the questions that we have today. So actually, from today's point of view, we would say, well, they understood very little, right? It was a whole bunch of new physics that was kind of not known to them, but they didn't even know that it was not known to them because there was kind of no glaring open question. So I'd really be curious to know how they perceived that situation and how they got to the point of opening the door to the quantum world and taking up that challenge.
Yeah, definitely. It sounds like a very fun dinner. Please invite me. So, well, awesome. Thanks a lot, Valerie. That was absolutely fascinating. We didn't talk a lot about stats, but I love doing these episodes from time to time, where we de-zoom a bit from stats and just talk about fascinating science in general. I think it's very interesting and also quite important to put more rigorous pedagogical scientific content out there in the world. We've seen that in the recent years. So thanks a lot for doing this for us, Valerie. I will put a link to your website in the show notes for those who want to dig deeper. Also, feel free to add any link to cool papers or experiments or videos that you think listeners will appreciate. And thank you again, Valerie, for taking the time and being on this show.
Thank you, and rest assured that stats is still at the basis of all this, despite that we took a more high level approach in this discussion.
Yeah, for sure. Well, thanks a lot, Valerie, and see you soon on the show.
Let me show you how to be a good breezy and change your predictions.